So you're seeing Badgerland User Group. We're a Milwaukee-based user group, Wisconsin. This is our summer event, Summerfest, which just ended, music festival. We've got James Christ from EngineSoft, who'll be speaking a couple minutes after noon. Would like it to end by 12:55. And if it ends earlier, if there's not enough questions, that's okay too. Everybody should be muted, and we're going to try to monitor the chat, and it should get posted this afternoon on our Facebook, LinkedIn pages, and then over the weekend on our website. So Badgerland User Group was established in 1994. We used to have 3 meetings a year. I'm looking into the possibility of doing another in-person meeting next spring at Manpower. I don't know if they're even renting out that convention space anymore, so I just made a preliminary call on that yesterday. So here's Wisconsin. Most of our members are Milwaukee, suburban Milwaukee, but we also get Green Bay, Madison, some people from Chicago come up. We've got membership dues. This year our dues and last year our dues are half off because we're not meeting in person. We're meeting virtually monthly. And one way that we do try to get people to pay, so we're like, 3/4 of the year done, and a lot of companies haven't paid yet. And so Bruce and I are volunteers. So one of the ways that we get people to pay is by having these door prizes. You have to have your yearly dues paid. And that does help get some of our dues paid, so we don't have the time to follow up with everybody. So this month, we're giving away a Milwaukee tool set, and I've had, 5, 6, 7 people say that they're interested, and we've checked in to see whose company has paid dues, and so that reduces it by a couple. So we'll determine this afternoon who wins and announce that on our Facebook page. And here's the Milwaukee downtown headquarters. We also go to Blue Harbor Resort in Sheboygan. So PTC user, I don't know, some people have found out about these lunch and learn sessions by PTC user newsletter, which comes out monthly. So it is a really nice newsletter with lots of links for training and different things that are going on with PTC products. So you just have to go to ptuser.org, log in with your email address and create a password, and then you're in, and then you should get that monthly newsletter. As you see here on the main page of PTC User, there is an in-person event for the first few days of October, 3rd to 6th, with training down in Orlando at the entrance to SeaWorld. It's going to be a really nice, we should get between 300 and 500 attendees. There is not a LiveWorks this year, so we should be getting people maybe that would typically go to LiveWorks that would come to Orlando. Any questions? Deborah.l.white@gmail. You can friend me on LinkedIn if you want. We do have LinkedIn and Facebook groups. Just search for Badgerland User Group. The only other announcements I've got here is that tomorrow, July 15th, Friday at 11 a.m., we've got our CAD Windchill admin sessions. So if you or one of your coworkers administers Windchill or CAD products, Creo or other CAD products, this is just a open roundtable that we've got about 15 people who have been attending monthly to discuss how, these people work their magic with the different users that they've got in implementing Windchill and that type of stuff. So if you want more information on that, just email me and I'll give you the link. That's all I've got. I can turn it over now to James Christ. I think I saw that he's on. I'll try to watch the chat, but if I can't, then maybe just need to say something verbally. So I'm going to stop sharing right now. And turn it over to James. Thanks.
Thanks, Deborah.
Sure.
Let me go ahead and share my screen. So I'll try to keep an eye on the chat as we're going through, but with PowerPoint Presenter View, I might miss something. So Alana, if you can keep an eye on the chat and jump in if there's anything more time sensitive. Right. Can you let me know if you can see my screen?
I can, yes.
Okay, perfect. So I appreciate everybody joining today. This will probably be more like a 20-25 minute talk, and then plenty of time for questions after, and then we might even get you out of here early. So this is a very wordy title. Let me jump into the agenda. So the kind of four main points that I'm going to hit during today's presentation. First, a brief introduction to who NGINSOFT is, and then the bulk of the presentation is going to be kind of an introduction to multi-body dynamics as a general topic. And then I'll do a little bit of kind of compare contrast between the professional tools that we carry and some of like the CAD embedded tools like Creo Mechanism, which you might be more familiar with. And then I'll close out with an interface that we have between Recurdyn, which is a professional multi-body tool, and Creo. And that's kind of why we're talking to you today. So who is NGINSOFT? NGINSOFT USA, obviously the company that I work for, is part of a multinational company founded in the mid-'80s by a group of engineers. It's always been engineering-led, and for our entire history, we've focused on CAE technologies. So today we have over 200, I keep meaning to update this slide, it's over 300 experts in technology, over a huge array of different CAE disciplines. But we are very focused on simulation, software, and consulting, basically. And we do a lot of customized solutions for customers and working with academia as well. At a very high level, you can see over 4,000 consulting projects, over 1,500 software customers, 130 trainings a year, and over 60 research projects with academic groups. Through these. Right, so this is kind of a high-level overview of the different core competencies that we have. So you can see probably something that you're interested in. We spend a lot of time on fluid dynamics that we're not going to really be talking about today. So we will be talking kind of optimization, multi-body dynamics, HPC, that sort of stuff all kind of wraps into the multi-body realm. All right, so starting off with kind of what is multi-body at a very high level, and it's a system level analysis tool. So, and you'll hear me refer to it as MBD, and I kind of apologize. I know that has a different context in the CAE or the CAD world versus the CAE world. But for the CAE world, that means multi-body dynamics, which I said is system level, and I'll go into each of these in more detail. But it's really comprised of three main things: kinematics, contacts, and multi-physics integrations. So that's what really lets you do the system level analysis, is by coupling this kinematics and contact solver with, a CFD solver or an FEA solver or a control system, for example. All right, so what is the kinematics portion of this? This is the simplest part, and it's the part that is kind of hard to screw up. So every multi-body tool that you'll ever encounter will do rigid bodies pretty well. This is really the dynamics one type of stuff, where you have, some simple object and then another object rotating about the center of another one. So it's a lot of coordinate system transformations, but at the end of the day, it's pretty simple math. It's just very tedious and a lot of that simple math. But the key thing with rigid bodies is that you're not discretizing the object like you would for FEA. So you can reduce every body in a system to just a local coordinate system. And then you connect those coordinate systems with joints. That's what this really simple example is. We have a bunch of linkages, and we're connecting them at these circles here. So we're connecting to ground with a revolute joint, gives us 1 degree of freedom in rotation. We have the same thing on this side, and then we have a spherical joint over here. So that means all of our translational degrees of freedom between these two objects are fixed, but it can rotate about any degree of freedom. All of the rotational degrees of freedom are open. And then we have a UV joint or universal joint for this one, so that's a slightly more complicated set of degrees of freedom, but same basic idea. You've got points connecting two objects and some number of degrees of freedom. And then also forces are going to be found in every MBD tool. So that can either be a linear force or some radial force or a torque, or simple springs would be handled here as well. All right, now jumping into some of the more complex stuff, the contact. Before I go into these examples, I want to do just a brief intro into how these solvers are handling contact. And we use what's called a penalty method. And what that means is, let's say we have two objects, so we're zoomed way in here. The solver is going to have some search algorithm to figure out when two parts are overlapping. And then it essentially inserts a virtual spring between these two objects to resist that overlapping. And these, because it's a spring in reality, the repulsive forces are going to be proportional to how much of an overlap there is. So you can see sort of a more complex example here, and then a more simplified example here. In this case, we're seeing the discretization that the solver is using to evaluate contact. So for a sphere, it's actually super simple because you just care about what the center of that sphere is and what the radius is, and from that you can figure out if it has a point intersecting with this other object. But this one, the box here, has to be discretized to some extent. The solver is going to handle this a little bit differently, but in this case, we can see that it's been tessellated and it's using these facets to evaluate contact. Now that we've sort of gone over some of the basic components that go into a multi-body solver, I'll go into when you would want to use a dedicated tool versus something that's embedded like Creo Mechanism, because they each have their own use cases. And I'll go through each of these in more detail, but it's basically contact-driven problems, flexible components, and the multi-physics problems. That goes back to the integrations that I spoke about earlier. And then lastly, automation. So for contact-driven problems, kind of self-explanatory, but this is really what separates a kinematic solver from a true MBD tool. For a dedicated tool, that's kind of their selling point, so you'll find much faster contact algorithms in the dedicated tools. As an example, this is a super simple problem that I set up, and it solves in 10 seconds to do 5 seconds of simulated time. So for simulation, that's almost real time, right? And this is actually a deceptively complex problem. When you have a box like this, it's very easy for the solver to see, one singular point penetrating the bowl that it's in, and generate far too high of a repulsive force. So for tools where contact isn't their strong suit, you'll generally see the box explode out of this example. Anytime I'm testing a new solver, this is the sort of thing that I do just to get a feel for how stable it is. And for a more kind of realistic example, I found this bike chain. The actual simulation is looking at switching gears for a bike chain drive. But if you think about what the solver has to do here, it has to evaluate contact between every single one of these links and each of these sprockets here. So that's, quickly becomes hundreds of contacts to evaluate. And if it's not efficient at doing that, it's going to sort of choke and not make any progress. And the other thing you'll see is a lot more customization with how you can define contact in a dedicated tool versus a CAD embedded tool. So the CAD embedded might have, you know, half a dozen contact types that you can define, whereas a dedicated tool, this is just a subset of the analytical and semi-analytical methods. These are more efficient because you can reduce the problem set a little bit. Best example here is sphere-to-sphere contact. If you can simplify your problem to being just 2 spheres, then, like I said, you just have to evaluate the distance between the center of those spheres to know if there's contact, instead of doing a full tessellation of the object. And then next, so flexible components. This is most commonly handled by coupling with a separate solver. In the case of Recurdyn in particular, it's all handled by one solver. There's sort of a couple of different ways flexibility is handled. The first being linear flexibility. You might see this described as the Craig-Bampton approach. Recurdyn, we call it RFlex, but this is the general name of that method. And without going into detail, basically, it's a linear approximation of this object. So it's quicker to solve, but you can't handle nonlinear problems. You can't do contact between RFlex bodies or Craig-Bampton bodies. But for something like this, where you just need some small amount of flex, then that can be a suitable approach. Then there's the FEA type approach. So that's going to be your full nonlinear, often coupled with a third-party solver to handle the flexible component. Like I said, with Recurdyn, it's all handled by one solver. That's sort of its unique selling feature. In this case, we can see self-contact with this spring. So if you have very sensitive springs, or you're looking at very fine detail, and give you a better result than just using a simplified spline curve to describe that spring. And then similarly, you'll see differences in the way that you can interact flexible bodies with other flexible bodies or rigid bodies, depending on the solver and depending on its capabilities. I don't have the video. I've been meaning to put it into this deck. But this is a great reference example that one of my coworkers did a while back, looking at the boot on a CV joint. And in their benchmarking, they were able to perfectly replicate the buckling behavior that you can really only get by doing a full nonlinear flexible simulation. You can't see it on this side, but on the other side, there's a ton of self-contact happening. So you have to have a really robust contact solver to be able to deal with that. Next, I'll talk about the multi-physics integrations. So something like Creo mechanism, it's really not designed to handle this type of problem, right? But as you move on to the dedicated solvers, you'll generally have a ton of built-in integrations where you can sort of just click a button and it takes care of everything behind the scenes to do a co-simulation between the two solvers. And the most common things that we see people using that for are a fluid simulation. In this case, we have a coupling with ParticleWorks, a particle-based CFD solver. So if you wanted to look at churning losses in this gearbox, for example, or material handling problems are pretty common as well, coupling with DEM solvers. You could evaluate, for example, how much force does it take to move this assembly here. And lastly, this one combines a couple of different things, including a control system. So we can either do using the built-in control system tools, or coupling with Simulink is probably the most common thing that people are using. Lastly, on kind of the big difference between dedicated and built-in solvers is automation. And it really comes in two different flavors. The first being automatically setting up your problem for you. So that's kind of what this is showing here. Recurdyn and really all dedicated solvers will have some sort of toolkits for building certain types of assemblies. So if your problem fits into that toolkit, then it saves you a ton of time. For example, if you had to manually wrap the chain around this set here, that'd be a huge tedious task, right? But if you can click a couple of buttons and it does the wrapping for you, then saves you a bunch of time. And the other thing, and this varies based on the use case, but the dedicated solvers will typically have scriptability baked in. So some way of either automating a process or adding functionality to the solver, maybe custom contact definitions, anything that you want to do, these tools are generally built to allow you to do it. All right, so I've talked up why you would want to use a dedicated solver, but there's always, cons to every pro, right? So when you switch from the embedded tool in your CAD system, obviously Creo for everybody here, and then go to a dedicated tool, there's challenges associated with that. The first being geometry. That's kind of a catch-all for all of the tedium involved with moving data from one tool to another. So you pretty much are always going to have to do some amount of CAD cleanup, whether that's removing all of the bolts in your assembly or simplifying some surface for better contact performance. Whatever the case is, you have to do some amount of cleanup. And you lose metadata. Metadata, again, being sort of a catch-all for stuff that you wish would go from one tool to another, but doesn't. A good example for this would be if you had joints defined in your Creo mechanism model and wanted to step up to a dedicated tool for some reason. You're generally going to lose all that information. You'll just get the geometry to come over. And revision control is difficult. So this is sort of at the enterprise level. You're losing the parametric relationship between your simulation model and your CAD. So figuring out when changes have been made to your CAD model and then applying them to your simulation model is sort of a whole task on its own, especially when multiple people are working on the same project. And really, as a byproduct of all this, you end up duplicating a ton of work every time you want to make some change. Now, obviously, the reason I'm talking about these downsides is we think we have a pretty good solution for a lot of them, and that's what we call the Creo-Recurdyn Interface Extension, or CRIX. And these are a couple of text-heavy slides, and then I'll switch over to a video demo. But the idea being, if you want to take, we want to help you take as much of your Creo data as possible and move it over to Recurdyn, the multi-body tool that we carry, in as few steps as possible, and then be able to make any updates again as quickly as possible. So you'll see that the export process from Creo is very straightforward, and you end up with a portable file, which I'll talk about as we're going through the video, why that's important. It'll automatically launch Recurdyn for you. Do merging of bodies into subassemblies, or you can merge a single subassembly into one body, and that'll make more sense when we see it in the video. And if you're using mechanism-style constraints, at least that's what I'm calling them. I'm not sure. I think PTC calls them constraint sets, but to me that's a little bit less descriptive. So if you're using like the pin and slider, those sort of constraints versus the more CAD ones or more geometry-based constraints, we'll be able to reuse those in the simulation model. And then the biggest thing is updating that model anytime your Creo model updates. It should be easy to apply those changes to your simulation model. This is the workflow that we'll kind of step through in the video. We export our assembly from Creo. That's a very simple dialog inside of Creo. And then there's an import process on the Recurdyn side. So the first time, it's a little bit more work. And then when you do subsequent updates, it's a lot easier. So between importing the model into Recurdyn and actually having to update it, there's a bunch of stuff that you have to do for any MBD model. Making sure all of your mass properties are correct, add joints that were in the Creo model, and then setting up the MBD problem. So applying any contacts, forces, all that sort of stuff. And obviously, you simulate it, and we'll kind of skip over this portion for today because that's something that you have to do for any MBD model. And then we'll jump over to updating. So if we assume some changes were made in the CAD, either changes that we do or don't know about because they may have been made by other folks in the organization. Automatically find those and apply those changes to Recurdyn, preserving any of the work that you've done since the last import. If I jump into this video, I just want to check the chats. So this is actually a really fun example that I found on the PTC site. It's a Lego car and trailer assembly. So this is just kind of a fun example to use. But there are, I think, over 1,000 parts or over 1,500 parts in this assembly. So it's not trivial by any stretch. You can see I've switched over to this Applications tab where we have only one button in the interface. So you can't click the wrong one. And then it pops up this dialog. Okay, so there's 752 parts in this assembly. Let me let this play. So there's a couple of different options. By default, it'll just export everything that is visible in your Creo assembly. You have the option to specifically make an include or an exclude list. But the nice thing about only exporting visible objects is you can use simplified reps. So let's say you have a simulation simplified rep, excludes or hides all of your nuts and bolts and stuff like that. Then you're basically able to reuse that without any additional work. You just apply that and export the visible stuff. Optionally include or exclude the joints that it finds. Not sure why somebody would uncheck that, but we wanted it to be an option, so you can ignore those if you want. And then by default, it's going to open up Recurdyn as soon as the export finishes. So the export is done. It's written out a portable file. And what I mean by that is it's a single standalone file that can be shared externally. So what's happening under the hood is we do a kernel conversion so that Recurdyn is able to open up this file without any external dependencies. So somebody in the CAD department could perform the export for the simulation user and then send them over a single file, which they are then able to import. That lets you keep separation if you want it. Otherwise, if it's all happening on the same machine, that's obviously going to work. So it's parsing in that file. Okay, here we can see the import dialog. It's giving us a preview of the assembly structure that we're going to get once we actually click the import. And in 1 second, I'll show the. Been so many issues with this this video playback. So pretty soon I will right-click on one of the sub-assemblies, which you can see denoted with kind of a darker blue icon. That means it comes in as the simulation equivalent of a sub-assembly. We call them subsystems, but same idea. And what I did here was I right-clicked and said convert it to a body. And what that means is, as far as the MBD solver is concerned, it's reduced down to a single coordinate system. So I can constrain it with just one or a handful of joints versus needing to manually constrain every single thing in that subassembly. And there's no joints in this model, but you would get this. You would just get a list of any joints that are there. This takes a while. There's, like I said, a couple hundred parts in here, so it'll take some time to do the I/O. Forward. Now we can see that it imported everything. I'm going to do some graphic stuff to make it a little easier to see what's going on. You can see this is our assembly structure here. This is showing all of the parts that are at the top level. And then if I scroll down, you would see what we call subsystems. So that's highlighted in this yellow box here. Now I'm jumping into this subsystem, and we'll see a bunch of basically a different assembly structure showing what's contained inside of that subsystem. I deleted the animation on this video, and it keeps doing that. Word. Okay. Pause it just to what's going on here. So this is one of the components that I merged into one solid, basically. So inside, we still have all of the geometry features, all of the parts that are there. And that means they can be updated the same as any other part. But from a constraining perspective, we can just apply like one fixed constraint would fully define every part inside of this object. All right, so we're going to skip over the actual running and MBD simulation portion. So for sample purposes, we can see that there's one part. We're going to say that's the change we want to apply. This is sticking out too far, so I'm just, I skip over the actual geometry changes, but basically I just cut this piece here. You can see that that change is applied. And then let's assume that that change was made by somebody else in the organization. Maybe the simulation person doesn't even know the change was applied. So they could go through change logs and figure out, what changed. But you're liable to miss something, right? So by exporting the entire assembly again, it'll do that search for you and figure out any parts that have changed since the last import, really reducing any chance for errors. In this case, I know where the change is or which subsystem it's been applied to. So for the export, to make it go a little bit quicker, I hide everything except this subassembly. And then that's all that's going to be included. That shows that you don't have to export the entire assembly every single time, but it is an option. Then you can sort of see that that piece is sticking out there, and then it goes through, does the update. We have a couple of options to modify any updates as it's happening. In this case, it's just a click through, get that update to apply. And if I had contacts associated with that body or any joints, those are still going to be there. I won't lose any work. That's one of the key customer complaints that we received to develop this is updating geometry often leaves you deleting one thing and losing all of the associated contacts. And then you have to add them back in after you add in that part. So it's sort of a pain. And we wanted to automate that entire process. So that concludes that presentation. I am happy to take questions either about this interface in particular or multibody in general.
Does anyone have any questions? Feel free to unmute.
I thought about this last minute. So if you're interested in learning more about multibody dynamics in general, or Recurdyn in particular, we do have a tips and tricks webinar series that we do every month. These are quick. It's always under 30 minutes, and we try to do like 1 or 2 presentations about little features in the tool. And if you go to our website, enginesoftusa.com, you can just search for it in Google. It'll be the first thing that comes up. And then if you go About Us, CAE Webinars page, and you can do register now to sign up for that webinar.
So last chance to ask a question, even just a quick one or general one, whatever you want. Otherwise, we'll call it a day.
No questions, but good info. Thank you.
And I'm not sure if it's in the meeting event or anything, but if you have questions and you think as soon as you log off, you can always reach out to me direct. Either on our website, you can do something there. There's a bunch of forms you can fill out, or you can email me direct, james@enginesoftusa.com. Note that there's only one E in engine. That always trips people up.
Thank you so much, James. Anybody have any questions for me? Like I said, we'll try to, usually this recording comes back in about 30 minutes and then right away I'll post it on our Facebook and LinkedIn groups. And And then, like I said, over the weekend, it'll get on our Badger UG website. So the recording will be there if everything works out okay. We won't have a lunch and learn next month in August. We're gonna let everyone enjoy their summer, but then we'll return sometime in September, probably mid to late September, either on a Thursday or Friday, I'm not sure. So, you know, I'm open if anybody wants to reply, if you think Thursdays are better than Fridays, or because we have been traditionally doing Fridays, just let me know. So I'm gonna end the meeting for all. Thanks everybody for coming. Thanks James and Alana for helping set this up. I really appreciate your time. Bye everybody.